Hello everyone, welcome back to IMSE881 Linear Programming, Lecture 6. Today we're going to talk about duality theory. The contents is from the handout of page 47 to 60 of your handout. First, we introduce the concept of a duality. Consider the following linear programming model, okay, and we refer this as primal problem. Minimize C transpose times X subject to AX greater than equals to B and X is greater than equal to 0. Here we specifically using greater than equal to constraints, so it's easier for our development initially, and then we gradually generalize it. Since we have the greater than or equal to constraint, okay, so we're adding a so-called surplus variable right here with a negative surplus variable, as corresponding cost coefficient will be 0, and both the surplus variable will be non-negative as well. Look at our simplex tableau at the optimal solution, and with all the zj minus cj, which is column 0, are less than or equal to 0, either a negative number or 0 for the corresponding basic column. First, look at the green part. The original variable x1 to xn, and this is the zj minus cj corresponding to those, and the yj is the current tableaus, final tableaus is column. And the orange part is are the so-called surplus variable column, and they also have zm minus 1 to m minus m minus cn minus m. Same thing, we have the corresponding column below, and then here is the objective function right here, and below is the current basic solution. Okay, first I want you to pay attention to this original columns, the variable columns are corresponding to the original variable. For those, the original variable xj and their zj minus cj is actually equals to cb transpose times b inverse times aj. Aj is the column original corresponding to xj, and cj is the cost coefficient corresponding to xj. And we know that we define cb transpose times b inverse, we define as a variable called omega, and this becomes omega transpose times aj minus cj equals to aj transpose times omega minus cj. So here what we're trying to do is, since zj minus cj are less than or equal to 0, so therefore this is also less than or equal to 0, this part less than or equal to 0. So therefore the conclusion is that aj transpose times omega is less than or equal to cj. Okay, putting back to the matrix form is a transpose times omega less than or equal to c. Continue look at the orange columns, which is corresponding to the surplus or slack variable columns, ui, and I from 1 to m, so I have m of those. And look at their corresponding zj minus cj entry. Their zj minus cj actually is a zm plus I minus cm plus I. It's still equal to cb transpose times b inverse. However, since they are slack surplus column, so they have a negative 1. So the entire column will be a negative identity matrix, negative unit vector, and equals to minus 0 because their corresponding cost coefficient equal to 0. We know that cb transpose times b inverse equals to omega transpose, then becomes an omega transpose times the negative unit column, and minus 0. Actually, this equals to negative ui, omega I, negative omega I. And this part is less than equal to 0 based on the optimal condition, zj minus cj has to be less than equal to 0. And that concludes one thing. Since negative omega I less than equal to 0, so therefore omega is all positive number or non-negative number. And also, the objective function value, we can see that the z hat is the current objective function value equals to CB transpose times XB, and it also equals to CB transpose times B inverse times B, which is XB. And CB transpose times B inverse equals to omega, and therefore equals to B transpose times omega. So now, based on this, we have our corresponding do problem. The do problem. The yellow square actually highlight what a kind of conclusion we have. So our do problem becomes a maximization problem over B transpose times omega, and subject to certain constraint. The constraint is A transpose times omega equal to C. All right? And also, omega is non-negative. So this is what we refer as our do problem. So here we show you how we're developing a do problem from the primal problem itself and using these zj minus cj relationship. Next, look at it again. For the original variable x1 to xn, the original variable x1 to xn, look at their zj minus cj again, equals to aj transpose times omega minus cj. If xj is a basic variable, which is taking a positive value, I know that corresponding zj minus cj entity will be 0, and therefore xj times aj transpose times omega times minus cj will be equals to 0. Okay, this will later on refer as a complementary slackness condition in our primal and do problem. Look at the surplus variable section. The surplus variable from z, look at their zm plus I minus cm plus I equals to negative omega I. So if u is a basic variable, the surplus is a basic variable, which is greater than equal to 0, then corresponding omega I equals to 0. So here I'm going to write it down and repeat this again. So if base x is a basic variable, so that means x j is greater than 0. Then aj transpose times omega minus cj is going to be equal to 0. All right? Let's do. So here, if ui is a basic variable, and that means ui is greater than 0, and therefore omega I is equal to 0 in this case. So that gives me some kind of relationship to follow, okay? So therefore, the conclusion on this part is the do surplus, the primal surplus times the do variable equals to 0, okay? So that's another conclusion we have. Look at the example we have. Here we have a primal problem with a 6 times x1 plus 8 times x2, and 3x x1 times minus x2 is greater than equals to 4. 5 times x1 plus 2 times x2 is greater than or equal to 7. Both x1 and x2 are non-negative. Their corresponding due problem becoming a maximization problem with maximize 4 omega 1 plus 7 omega 2. And look at this part and that part. It's just a transpose matrix. So this is A transpose. So A transpose times omega equals to 6 and 8. So here what we have, if you look at this here, the primal objective function cost coefficient becomes the right hand side on the due. And the primal right hand side becomes the objective function cost coefficient in the due. Primal is minimization problem, and the due will be the maximization problem. These are the characteristics I want you to remember, and comes very handy. Also, for the constraint matrix between primal and due, on the constraint matrix between primal and due, I just transform them to each other. Also, later on you will see that if this is a greater than or equals to constraint, it will have non-negative due variable. If this is a non-negative, variable in the primal, and then we have less than or equal to constraint in the due. So here we look at this optimal tableau for the previous problem. Okay, optimal tableau. We have x1 and x2 are the original variable, x3 and x4 are the surplus variable, and current objective function equals to 42/5. Okay, and the current due solution equals to 0 and 6/5. Okay, because that's a negative due solution. So omega 1 equals to 0, omega 2 equals to 6/5 in that case in the pink area. Look at their zj minus cj portion. For the x1 is the basic column, so their corresponding zj minus cj equals to 0. Let's take a look, see if that works out. So z1 minus c1 equal to omega transpose times a1 minus c1. So 0, 6/5, that's the omega. And 3, 5 are the first column in the original problem. Minus 6 is the c1 equals to the cost coefficient for x1. So actually they equal to 0. Look at the z2 corresponding to x2 in my tableau. And x2 is not a basic variable. So let's take a look how that come out. So 0, 6/5 times 1, 2 is the original column corresponding to x2, minus c2 is the cost coefficient corresponding to x2, and that gives me negative 28/5, which is the zj minus cj right here, z2 minus c2. So also we can see that since x1 is a basic variable, the current value is 7/5 in my basis, and their corresponding z1 minus c1 equals to 0. So x1 times z1 minus c1 equal to 0. Take a look over x2. x2 currently is non-basic, so x2 equal to 0. And z2 minus c2 equals to negative 28/5. So therefore, x2 times z2 minus c2 also equal to 0. Let's look at the x3 and x4. x3, for x3 column, x3 currently is the basic, so x3 currently the value is 1/5, okay, 1/5 on our table. And then you see that z3 minus z3 equals to negative omega 3 equals to 0. z4 minus c4, which is z4 minus c4 currently is non-basic variable, so x4 equals to 0. So So Z4 minus C4 equals to negative 4 equals to negative 6/5. Again, we can prove that x3 times Z3 minus C3 equals to 0. That's fairly easy to prove. And second, the x4 times Z4 minus C4 is also equals to 0 in that case. So we proved that numerically, okay, these four conditions between the primal and dual relationship. Next, we'll look at some conical form. We summarize them together. So this is our primal problem, P, and this is our dual problem, D. And here what we have is basically the primal constraint corresponding to the dual variable and the primal variable corresponding to the dual constraint. For minimization problem, if your primal constraint is greater than equal to constraint, and your corresponding dual variable will be non-negative. If your primal problem, your primal variable is non-negative, and then your corresponding dual constraint will be less than equal to. This is just for this case we're developing, okay? However, later on we're going to generalize this concept later for other different situation. So here's the lemma. If x and omega are feasible solution for primal problem and the dual problem respectively, therefore we have a B transpose times omega is less than or equal to C transpose times x. So what I mean is the objective function of dual problem is always going to be less than or equal to the primal objective function. Okay, since primal is minimization and the dual is maximization. So how do we prove that? Also, for this we want to prove x transpose times A transpose times omega minus C equals to 0. Okay, and also we want to prove that omega transpose times AX minus B equal to 0 as well. So we proved that before, so now we want to sum it up together. First, based on the primal constraint condition, AX equal to B, and the dual variable, so this first green line over here, and we have AX greater than B, omega is greater than 0. So omega times AX equal minus B supposed to be also non-negative, because non-negative times non-negative is still equal to non-negative. So therefore we'll have a relationship by multiplying this together. So omega transpose times A times X, which is the first part, is going to be greater than omega transpose times B. It's going to be greater than B transpose times omega. From the dual constraint, right here, and the primal variable, we have the following result. A transpose times omega is less than equal to C, and X is non-negative. So these two multiplied together will be non-positive, okay? So therefore I have X transpose times A omega is less than or equal to X transpose times C, or C transpose equals to C transpose times X. So between these two results, what I have, I can establish a relationship, and B transpose times omega is going to be always less than C transpose times X. Okay? So finally, we're going to say, if then actually B transpose times omega equal to X transpose times C, then only if the equation 2 holds for inequality, and that's the optimal solution. But later on, I'm going to show you that. So this is a so-called conical form. This is what we call the strong